All right. And so today we are going to talk about some applications. So this might be something you can consider if you want to do the final project. Oh, by the way, I already posted the final project on Canvas. Go through that. It's very flexible. You can do whatever you want. So far, we have only covered Google Engine, but there's also database coming. So you can do either one of them or you can do both. So it's up to you. But I just want to post it in advance so that you can have some time to think about it. If you have questions, talk to me. So essentially, what you need to submit is just Jupyter notebook with text, with images, with maps, with code. So kind of like something in here like this. So you need to have a mix of text, source code, and whatever you have. Not this one, maybe where is it? Google Engine. So you can have multiple, or just look at some of the labs, like how I did it. You can have screenshots. You can have text, you can have source code, and I can run the source code if you want to. But your final product should look something like this, with different headings, different sections. So for the final project, you should have 4 sections. Like, why are you doing this? Introduction, and then what data do you use? How do you do the analysis, and what's the output? So it should be straightforward. And make sure you spend some time. Okay, if your notebook only contains like 2 lines of code, it's probably not enough. So think about it's 100 points, it's 2 lab assignments, and if you spend like only 10 minutes, then your quality is probably not good. Unless you're doing some create new package, you just 1 line of code, you can do a lot of things. But talk to me if you want to see like, oh, is this enough? I will let you know. But at least it should be something like address some real world problems. And what we're going to cover today might give you some idea, but there are a whole lot more. So I would encourage you to think about what's your um, research topic or your thesis or your dissertation or your capstone project, whatever. And if you use Google Engine or use database, and try to see how you implement those. And at the end, this should be just a notebook. So you're going to present your notebook, and keep that in mind. You don't necessarily have to run the notebook in real time trying to solve. You should basically have the code block just like what you are seeing in here. Or if you go to the sample solutions, the website, right? Have the text, have the source code, have the maps. Everything should be self-explanatory, so I don't have to run the code to see the result. Again, if you are not sure what to do, if you are not sure what the final product look like, just show me what you have and I can give you suggestion. Yeah, just Google Colab. Yeah, and then just have the notebook. Send the link to your Colab. Just like you're doing your lab assignment. But this time you need to add some screenshots or something inside the notebook, not as separate. So I just want the link. I don't want the screenshots because everyone will be different. So you might have a lot of maps, you might have a lot of screenshots, but you need insert into your notebook. If you don't know how to do that, just check out the the sample notebook that I provided. You will understand. And both you really don't know what to do, ask ChatGPT. Okay, how to insert images into a notebook, how into a markdown, how to insert some videos or whatever you want, text or headings. Okay, so you still have so it's until December the 3rd. You have how many weeks? 6 weeks. Okay, so you have plenty of time. Don't wait until the last day to do it. You will not have enough time. So think about that, and then you can start thinking about what data set you're going to use, what kind of analysis you want to do. So here for today, I want to quickly go through some simple applications, like what kind of things you can do and why it is so powerful, why it's so easy. So the first one here is doing like surface water dynamics. And so Google Engine has this global surface water data set. So if you look at this one, JRC, so right now I think we have up to 2022. So version 1.4, and this is actually one of the first. If you look at the paper, the citation, so this one was published in 2016. This is one of the first paper actually used Google Engine to do global scale studies, and was published in Nature. And it's the one of the groundbreaking. Besides the forest change, we're going to cover later, but this is the second one. This very high highly cited, and it's doing like global and it's very, very useful. So the data set, what they're providing here, if you look at the bands, so basically like, I'm gonna show you um, what kind of bands within there. So this is data from 1984 all the way to 2022. So basically every year, um, oh, this is just one band. So it's like the overall imagery, but we also have the monthly history. Anyway, just look at what the data look like. So I'm going to um, add a base map. Okay, so right now this is using Esri base map. So it's not Google base map anymore. So if you're using an older version, you might still have access to that. But now it's using the Esri base map. So here, what we're doing, we just select just the occurrence band. So occurrence means how many times that pixel was detected as water since 1984. So you can think about 1984 to 2022. Every month you have one image. So that pixel, every month it can be either detected by as water or as non-water. So it's basically 1 or 0, yes or no, yes or no. And if you combine all the pixels together, combine all the time series together, you will figure out that pixel was inundated or it was detected water how many times out of over 40 years. Yeah, 38 years. So basically 38 multiplied by 12, right? 12 months. So you can think about maybe let's say, let's just a simple example. For example, 500 times. After those 500 times, if a pixel was detected water as 500 times, it means it's water all the time, right? So you're gonna see it's very inundated all the time. But there might be some pixel, for example, along the borders or the edges of the lakes or something. Out of the 500 times, it maybe inundated only 400 times. That means the occurrence would be 400 divided by 500, you'll be 80%. So you're gonna get a value of 80. Okay, so it's the occurrence range from 0 to 1 to 100. So it is 100, it means it's water all the time during the past 38 years. Make sense? So you can draw a rectangle if you want. If you don't, you should run this one. It should give you just a sample map centered around this bounding box. That's why it's so slow. This is a simple operation. Okay, just zooming to this location here, and so this is the bounding box that I just drew. Let me turn this one off just to show you what it is. Right, so turn this one off, and if you zoom in, right, so this one the account shows you from 0 all the way to 100%. So do you notice some patterns here? So if this permanent water, it's dark blue. If seasonal or temporary water, is like kind of a light green, light blue. As I mentioned earlier, like this is 38 years data since 1984. Every month, like examine is like 500 times. This pretty much is all the time, always water all the time. And for this, less. So if you really want, you can come here, you can turn the data layer on and off. You can get a sense of what, right? So the dark blue is always water. That means those are more like permanent water. But if you zoom in, like this is our so-called the prairie pothole wetlands. And if you see here, you see one more time. But now it's actually water. But it depends on the season. So the water is actually very dynamic. And this is why in here, even now it sees it's water, but in some time in the past, it actually the water was not covering the entire wetlands. And this might be some one example. If you want to, another good example, I think is in the, let's see, ROC somewhere. Where's the ROC? Let me see if I can see. Yeah, this one. See this one? I believe it's where's the, let me see here. Location. I just want to find a good one. ARA. Okay, here. Yeah, this one. This is a famous one. Right now, you pretty much see it's like very light accounts if you turn it off. So in the past, this is actually just the whole lake. This is a bigger one. Now it's just um much smaller. Although here it doesn't show you much changes, but if you want, you can inspect pixel values. 81, and this you see 23. It's kind of a little bit light. 15. So in the past, this is actually the entire one was a lake. And now this one, it's hard to see because it's so light. But if you want, I think where do I? If you want, let me show you here, like what it is. Okay, so I'm going to come here, click this create time lapse, just to show you what it looks like in the past. So I'm going to import here, create this one. Okay, and then create maybe for this one combination 84 to 2023, and yeah, let's see what it looks like. So I'm trying to show you the image is being used to delineate this data product, so you can see actually how the water actually is changing throughout the years. Oops. What's the error message here? Is it? Sometimes that's what I can see here. 1 second. Let me. Looks like it is because the image is too big. Let me turn on a little bit. 30 seconds. Oh. Let me try this one. I need to look in there. It might be because the resolution is too low. Let me come here, and I can do the same thing here. Should be the same result. Move this one, and AI. Move this one. Okay, here, and I'm gonna just simply put something here, and then export it. Okay, you just need to be patient. Where is it? The downloads directory, and then select this one. Okay, done. And then I'm going to use maybe this default one. It might be the dataset is too big, so I'm going to maybe change to 2021. The start month, I just want a summer. All right, so let's see what we get. So basically, we have all the Landsat satellite images since 1984, and then based on each image, you can extract the water. What? I don't think it's that much. Something might be wrong. Let me see here. Sometimes Google like become the quota becomes smaller and smaller. So it used to be fine, but now sometimes you might run into error. But you can always try a smaller one or something smaller time period. Okay, this is annoying. Let me see if I have some other. I can show you. What else? Never mind. I think we're wasting too much time here. I will show you next time. This is actually it should work, and I'm not sure why it's not working this time. So basically, what we are showing here is that we um, show you the map water occurrence at the global scale. So this is entire data set. You can do it pretty much for anywhere you like. So if you want, I can maybe go to Tennessee here. You see the changes. Right. So clearly you can see if this like main river usually is pretty prominent, but if you are along like in the upstream, those are usually much more dynamic. And you clearly see here it's not perfect because this is the Landsat 30-meter resolution. It's not going to align perfectly with this. But when you're doing the global scale, this is what you can get. And the higher the resolution, the more computation, the more challenging to be able to use that. So with this, next, let's take a look at this one here. Just to show you, for example, the um, dynamics, so-called the image histogram, just to show you, for example, earlier, let me run this one more time so that you can see the map. So create a new map again, and then in here, I draw this sample area around. It's confused. Let me restart the kernel. I think something wrong with the I don't know. So what we are doing here is like if you want to do analysis for a specific area and you want to see how dynamic is the water for that area, you can just use this simple Gmap histogram and then give you an image. So what we are doing here is basically within this area, within this rectangle that I'm drawing, I'm trying to see how much of the water is permanent water, how many of those actually seasonal water, and because we have the occurrence from ranging from 1 to 100. So if you run this one here, take a look, it's going to show you, for example, how many zero pixels means zero occurrence, no occurrence, and you can have all the values. So basically it means these are all the area, the the area of each occurrence value. So 0 from 0 to 99, right? And so if you want, you can create something like this. I'll quickly show you histogram, and you can have an image, you can have a region, and then okay, something like this. So what does this really mean? Is like in this total area, how many pixels? So this is so-called a pixel count. It's showing you roughly how many pixels. It has like floating point. Just ignore it. It should be integer. The reason is because the scale. And then I do like this. So you have most of the water. Some of those are very dynamic, kind of seasonal. You also have a bunch of those that are more like permanent. So this kind of shows you the overall distribution in the area in terms of the water occurrence. Right. So these are how many pixels, for example, 28,000 pixels that were detected as water 96 times out of 100. 96% of the time. Like I said, we have 38 years data, and you can think about it like most of the time it was water, but they also like some of the smaller pixels. So if you go back to this one, look at it one more time, right? So if you zoom in, right, those are more like seasonal water. This is permanent water, permanent water. And sometimes you might also have cloud, so cloud actually remove. So it's actually not. So even you have 38 years, 12 months, it doesn't mean it's like 500 times. You might only have 300 times because other data might include cloud. So this is how if you want to specifically using this data set, you can try this one. So give me an image, basically the occurrence, and then it doesn't have to be. So in here, the image histogram, it can be any categorical data. It doesn't have to be water. So if you want to create a histogram, so if you have an image like a value of 1, 2, 3, 4, 5, whatever, it will automatically calculate the histogram for each value, right? And for region, for scale, and also X label, Y label, so those are pretty intuitive. Okay, and then you also have a title here, surface water accounts. And you can also save this one. So if you want to, for example, save this one to your computer, you can either click the download plot as a PNG. So if you click this one, it should download this one to wherever you want, and then you can open it. Okay. Looks like this. So tiny. So if you want, you can uh, update a little bit. So here shows you, for example, auto size, because if you download it, click the download icon, it will auto size, so it's much smaller. But I can specify, for example, the width and also the height, and also the margin is like when you download as an image, you want to have something along the border so that it's not exactly um, basically give some space between the figure and the border. Then you can create this one so-called right image. Okay, you can also have a scale. So the larger the scale, the larger the image. And let's run this one. And you should save this one to your, oops, I think you need to install a package, I think by default, yeah. So you need to install this one. This is not, it does not come with the package. It's not a required dependency. So if you want to be more, you want to create some high quality, okay, of course you can take a screenshot if you want. You don't have to install this package. But if you want to like more control, then I can do this gmap, create G, and then just paste in enter. So this is called Kaleido. It's a package that you can especially save some figures from Plotly. So under the hood, all of these are created using the Plotly package. But it makes it so much easier to use because it is only one line of code. So again, let me you need to restart the kernel. It's annoying, but it should work now. So and then just run all kernel run up to the selected cell. It should take a couple seconds, and then you should have this high quality figure saved to a computer. And like I said, the image histogram can apply to any vector and any raster that's categorical. So even you can do it by length cover. So if you're trying to calculate, for example, the length cover type, you can use zonal statistics or you can use something else. So here you see it's done, and now let's come back to here. Refresh, task modify, water accounts, double click. You see, is it so much bigger? It's much better, right? So now you can insert, for example, if you're doing some analysis for your final project, you want to create some high quality one, of course you can. So now, oh, is it still the same? It might be just you need to zoom in a little bit. It still looks pretty sharp, right? So this is the border here. The margin is where the upper left, lower right on the border. So you can have a X label, Y label, and also the figure. So this just shows you the pixel count. So you can at least you can see the percentage, how many of the pixels are seasonal water, how many of the pixels are permanent water, and it's all one line of code. So try it out. Next one. So earlier I only show you the occurrence, basically the total. But this data set also has the history. So this one is called monthly history. And it's going to show basically this is an image, but the image has how many bands? Let me see here. System index. So 454 bands. So basically starting from 1984. What month? 1984 March. Right? 1984 March, April, and then all the way every month until 2022 December 2022. So in total, we have 454 time periods. And then if you want, you can aggregate, for example, see here, aggregate system index is going to show you, for example, the first image, the first band is 1984 March, and then blah, 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 all the way to right now. So if it goes all the way to the end, you should see December 2022. December 2021 actually. 2022 is not included, so it's exclusive. So in total, we have 454 bands within the image. And each image again is a binary, yes or no. So it's if the yes is detected water, otherwise it's no water. So let's look at this one here. And now I'm going to create this map just to show you what the image looks like. So here, this is only just one time period. So take a look at this one, right? We filter the image, and this one is basically August 1st to basically it's the month of August 2020 in this area. So now you see this is pure blue color. That means if this blue color, that means it was detected as water. If this um, yellowish color, there's no water. So this one different from the previous one I show you. This one is just yes or no. This one is no transition. There's no a range from 1 to 100. It's just 1 and 0. So if it is 1, it's water. So that means this is just for that specific month in August, August 2020, that month. And this is just the image. And so if you want to see, for example, the monthly switch within this area, look at this one, right? Pretty cool, just one line call. So what this one is showing you, um, basically for this entire area, we calculate the total water area since 1984, March 1984, right? So think about every month you have one image of water or non-water, another month water, non-water. So you can always calculate the area for that specific month. And you're going to have all the data points since you can zoom in a little bit, right? Why we don't see 12 months? 1, 2, this is April, March, April, May, all the way until October. Right, so we have 7 months. What happened to the other months? What's going on? Why it's all zero? Say it again. Yeah, turn into ice. Yeah, good point. Yeah, because it's in the north. So this is in North Dakota. So if you zoom out a little bit, during the winter months, it's just ice, snow. If they cover by ice and snow, the satellite is all white, so it doesn't know where it's water or not. That's why you don't, it's excluded. So in that data set, you don't see water in the winter months. And that's pretty much like in here. If you zoom in a little bit, there's no data because it's excluded. So mostly starting from April all the way to October, and some you might have some November, but it's very rare. So usually it's put from August to October, and that's why you see some gap in here. And for this one here, you're doing by you can specify what months do you want, right? So you can say, okay, I want the data starting from June to May. It's more consistent because when it's in April, right, the ice does start just melting, and you will see this water is much smaller. So it's like not consistent because it depends on the season. If you want to like figure out the water area consistently, you want the months that you are doing the same comparison, because April is like an outlier. So sometimes it's like melting a lot, you will see a larger area. If not, it's pretty small. So what we can do here is we just only do the data from June to September. So this to give you a much better, right? Now it's more continuous, but still you have some data gaps in here in the early days, because at the time there's only one satellite. And it is all cloud, there's no data. So still you want to have some gaps in a specific month. So for example, in 1985, June, there's not much data here. So it's like still it's empty. But this at least give you like, or even here, even in 2014, right? At that time was only Landsat 5. Or Landsat 8 also was launched in 2013. But again, it depends. If you have cloud, it's going to have an issue. But overall, you see the pattern, right? What's going on in the area in terms of water? It's slowly increasing to make it getting wetter and wetter. And this is starting from the months of for each year, from June to September. But you can also do some aggregation. So similarly, JRC histogram water 30 meter by year, you can specify a reducer. If you have special reducer, it's going to aggregate, because this one we don't have the reducer. And want this one to see what it looks like. So what this one is doing is, if you provide reducer, it's going to aggregate the data for that specific year using the data from June to September, right? So now instead of having four individual data points, for example, for this, we calculate the mean for all the data within the same year. And this right now is more continuous, right? So now you don't see the gap. So more like depends on what you want. If you're trying to see, okay, is the water increasing in this area? Yes, overall, you can see the pattern quite clearly since 1984 to right now. And every year, if you aggregate by year, it's more stable rather than if it's just simply doing by months. Certainly, that sometimes 1 month is zero, doesn't mean that the water are gone. It just means that there's no data for the specific months. Make sense? So if you imagine this, you can do that for vegetation, you can do that for forest, you can do that for urban, you can do that for pretty much anything. So this just give you an example how you can analyze temporal changes of remote sensing data. And you can also do the max. So earlier the reducer we use the mean. So basically means like calculate the mean of, for example, for all the months within the same year. But sometimes you might want like, okay, I want the maximum rather than the mean, because you want to see, for example, every year what's the maximum water area for the area. And you will see pretty much they're quite similar, because when you have more data points, when you aggregate, it looks pretty much the same. Yeah. So it's up to you what you want to aggregate. Make sense? Right, so this is how you do surface water. You want to change the surface water dynamics. And there's another section here called mapping flood extent. We don't have time to go over, but it's quite similar. So basically, rather than using the existing data set, they do the changes and analysis. This one is more like if you have any natural disaster, like new events, there's no data for that. So if there's some floods that happened this year, last year, it's not included yet. So in that way, you have to do the aggregation. You have to delineate the water by yourself. So this is a little more work, but it's certainly doable. You can follow it. So for example, for your final project, if you can do something like at this level, yeah, it's good enough. But you can use existing data set, and this one use SAR data and also optical lens data. It's a bit complicated. I'm gonna skip it, but you can follow instructions. You just run through, you understand what it is. So next one I'm quickly go over is the forest cover change analysis. So similar to surface water, right? You have the data set, you can analyze the changes. There are also some existing surface water data set. So forest cover. So this one is actually the first paper using Google Sensing to do global scale studies, and it's keep updating. And this one's published, the paper published in 2013, I believe, in Science. Yeah, 2013. So if you go to this one like get tens of thousands of citations every year. Let me just maybe do a quick Google Scholar. Where is the Google Scholar? Let me copy this one. To be somewhere on Google Scholar. Here. So 2013, you probably still in college, right? 2000 here. Oh no, what happened? No, this one. Sorry. To be this, copy this. You see the number? Web of Science. Oh, this one here, cited by 10,400 and 10,000, right? So it's 10 years. Every year get 1,000. So it's one paper has more citation than many people the whole career. Yeah, so if you really use some of the this kind of cloud computing and then do large scale that's nobody has done before, you can probably you can create something that's being used by a lot of people. Even the web of science gets 6,000. So this is quite amazing that how they we click here like this guy here this paper. So it's UND. I think for each paper you should also be able to see the citation here, just like in here. Okay. So every year you get like over 1,000 citation. Just to show you like some of the potentials. So if you want to like go for academia, yeah, you use some of this cloud computing to do some innovative, creative stuff. And so this is just one paper, and the other one I show you earlier, like for example, the surface water, also quite high. Let me show you here surface water changes. I think this one is a couple thousand, but it's still quite a lot. Okay, 3,000. Anyway, so let's quickly go through see what kind of things you can do. So forest, I'm going to load the data layer. So this one here, this specific data, so they have data since the 2000 all the way to I think it's 2021 right now. So over 20 years of data. And so in here, it shows you the forest coverage in 2000 and also the loss and gain and when it was lost. Also the original image. So the first year and also last year. So you have all the spectral bands in here. So basically it means, so you have data every year and since 2000, 2001, 2002, all the way to 2021. So every year you have one image. And then it's going to show you when, in that pixel, when the forest was lost. So let's just quickly run this one just to show you what it looks like. So the first image, maybe just, it's easier to show you what the data looks like before. So here, right, look at this one. So this is the tree cover. It also hits a percentage, similar to the water, like 0% to 100%. But this one is basically within the same pixel, was the area of that pixel was covered by forest. So you see is use some lighter color. That means they're not a whole lot of forest. For brighter color, blue, green, it's forest. So here, I think you need to maybe change the base map to the satellite base map so you can see the changes. But actually, it's here. You can do it. So let me download this one, like 2000, and this one. So take a look at this. So right now the tree cover, this is basically the image from 2000, the year of 2000. And so the tree cover is delineated based on that year. You're going to see, let me turn here. Is it pretty good? Right. So this one is a satellite imaging. This one is the tree cover delineated based on that imaging. And it's at a global scale. So you're welcome to zoom in and zoom out to see what it looks like. And what we are trying to do here is that, okay, 2000, you have one image. And then you have the tree cover. And then every year, they delineate the forest area and then try to figure out the changes every year compared to the last year. So right now, this is just the images in here. Let me see if you can zoom in more a little bit. Okay. So for example, this is the forest, and this is compared to 2000. 2000. So this is the same year. And then I can turn this one off. So this is 2021. Do you see any changes? All right, let's certainly let some loss. For example, in this area and somewhere in here. All right, so now if you change, you see this one, it's probably not the same anymore. See that? So those are kind of forest change. So what we are trying to do here is to see how much it changed. But this forest cover is only the year of 2000. It's not the current one. It's not the year of 2021. And what we can do is to do a binary analysis. So the binary means forest cover. So in general, if it's more than 10%, it's being considered as forest. So now basically we turn the forest cover into a binary image. So take a look at this one. So now it's a binary one in here. The green color. So you turn on this one, see here. So any pixel value greater than 10 are being converted to forest. So every pixel. So basically, the forest cover is the value range from 0 to 100. So if it's greater than 10, that means that pixel has more than 10% of green vegetation is being treated as forest. So in that way, you can do the calculation. Basically, this is just the simple thresholding. And with that, now you can simply run this one just to show you when the forest was lost. So the lost year shows you when that pixel was lost. And so the value range from 0 to 21. And you see this one here, 0 to 21. So what this really means is that if you see the yellow color, that means it was lost in the early days. If this red color, that means it's more recent. Okay, so the lost year is basically ranging from 0 to 21, starting from year 2000. Okay, so if the value is 1, that means the forest was lost in 2001. Okay, year 2000 is the baseline. So if the value is 10, that means the forest was lost in what year? 2010. Okay, and then the same thing, 2022. So if you really want to see like something in here, oh, there are a lot of forest loss, right? So this one is more recent. Yellow one are more in the old days. And if you see here, okay, what's this? Is this the national forest? But just the data set is not always accurate. Just to show you, like, this is how you can interpret the result. That means if you look at this globally, right, trying to see what's this, like in Russia, there also a lot of forest loss during the past 20 years. So with this data set, now you can start doing some analysis, and you can also do forest loss and gain. So it's not just loss. There are also some with new forest coverage since the year 2000. And let me run this one so you can add a new data set. And this one right now is it down here? Forest loss. So basically you now have two data layers. I probably need to turn on the loss here. Right. Although it's using the same color, but now we separate them. So for tree loss is the red color, tree gain is the the yellow color. So that means you can clearly see like yes or no. So basically from compare year 2000 to 2021, right? In that 20-year time period, some forests were lost, some forests again. So the red means it's lost, yellow means gain. So you kind of have the mix. And this is not always accurate. So it depends on the data, depending on the season. Sometimes they're not always accurate, but just for demonstration, this is what shows you at the global scale for the forest loss and forest gain. And yes, it's already in the database. So they already calculate. We're just plotting the data. And one question you might ask, for example, like, which country lost the most forest? Or which country gained the most forest? Or you can ask question like, which US state lost the largest area of forest? Which state gained more forest, right? So you're trying to get some idea. So here we're loading the country dataset, the country boundary. And then we can use this one, so-called zonal stats by group. So you remember previously by group, so basically the tree cover being, so this one is basically anything greater than 10% is like tree. So this one is addressing the question of, at the global scale, which country has the most forest? We're not talking about gain and loss yet. We are just talking about in the year 2000. Every country has some forest, right? So if you have to guess, which country has the most forest? Which one? Which country? Brazil? No, I'm just in total area. Which one? It's hard to tell, right? Just one, this one. So it's Russia. Right? I can tell the others, like Russia, Brazil, Canada, US, China. So you can see basically in here, if you take out the other category, that means, or even you can put it in. So that means overall, in the year 2000, Russia, the forest area covers was the almost 18.4% of the global coverage, right? Like I said, think about it just like an example. You can do forest, you can do vegetation, you can do agriculture, you can do urban, you can do all kinds of things you want as long as you have the data. But once you output a CSV, you can just create a pie chart, or you can create a bar plot. Do the same thing, right? Russia, Brazil, Canada, and it's all interactive, so you can zoom in and can zoom out. Just one line of code. You can also do this one. Now we're doing the forest loss, right? The tree cover is yes and no. Forest loss is also yes and no. So that means this one is trying to answer which country lost the most forest cover during the last 21 years. So basically, it's aggregating all the forest loss area as yes or no. So earlier I showed you the year, right? When it was lost, for example, 2001, 2002, or whatever. As long as the forest was lost sometime during the past 21 years, it was yes, it's a yes. And then if you aggregate it all together, you can figure out which country lost the most forest. Okay, so which one? Which are your top three? Russia again? Yeah, Russia is most. Yeah, it makes sense. What else? What else? Brazil? Canada? Yeah, total. So let's take a look. Yeah, kind of similar. Like the largest country like lost the most. But again, this is just, I mean, the demo. It might not be very accurate. The dataset has some issues if you look into in detail. But okay, so overall, Russia, like for all the forest loss during the past 21 years, Russia accounts for almost 17.5%. And then Brazil, US, Canada, or Indonesia. It's surprising. Yeah. And China, Congo, something like that. Similarly, you can do a plot, right? So just to give you some idea, like this is some of the global scale analysis. And right now we're only using the data set. But imagine that you develop some data set, for example, whatever feature you want to study, and then you use this to do global scale study, because this one doesn't matter how big is the area, you can do it very, very easily. So think about your project, like if you can do something like this, you can showcase the data, you can do some analysis, you can create some plot like this. And that's great, right? So it can be, for example, forest. You can also do agriculture. You can do wetlands. You can do whatever you like. And the mechanism is the same. So the workflow is pretty much similar. So look at the Google Sensing. It has tons of data sets. See if you can use some of these zonal statistics, create figures, plots, and try to showcase the changes of anything that you are interested in. And it's a couple lines code. It's not so very complicated, but you just need some patience to figure out what data you want to use, how to visualize that, and how to run some simple analysis. There are a lot more complicated ones. So Google Sensing is very powerful. So far, we only cover probably 0.1% of what it can do. There are a whole lot more. We don't use a whole lot of functions. Gmap, like we only cover maybe, I would say 40%, 30-40% of what kind of thing you can do with Gmap. But again, there are a whole lot more. I think I will stop here. And there are two more sections. I will leave this to you. And I think starting from next week, we do database. Okay, so bring your computer. You want to set that up, but the recording should also be available. Okay.